Okay.
Okay, hi. So what am I trying to say here? I just want to frame what we're allegedly doing here before John takes over and does it some different way. So so we've got this project to understand the exponential sheaf sequence of an abelian surface, particularly in the generic case, because there are things we don't understand about it. I don't understand about it. And right, what the generic case, particularly in the case where the Néron-Severi group is of rank less than 4. And we would like to have a really specific example of that to focus on, to understand. And we have a really good suggestion at the moment for such an example, and that is the abelian surface that's the product of the Gaussian elliptic curve and the Eisenstein elliptic curve. We have good reasons to suspect that that is like rank 3 or something. In its Néron-Severi group is rank 3, and that would be good material for us to understand. So this is, we're actually proceeding. We've been sort of trying to get to this point of, for weeks and weeks now or something like that. But we're really just about right there ready to really try to understand this particular abelian surface and its Néron-Severi group, and then all sorts of things flowing out of the Néron-Severi group connected with the exponential sheaf sequence and gerbs and stuff like that. And so since we're making such good progress, that means we can take a big digression right now. And the big digression is, for one thing, John came up with this suggestion by thinking about Néron-Severi groups of abelian surfaces in some generality, and thinking about them in terms of Rosati involution and what do we call that? The Jordan cone structure, everything like that. So I really want to find out about this. I want to hear about this from John. This is not really it's a good digression, or maybe it's not even a digression. So I want to hear about this from John. I want to try to interrogate about a lot of things, but we'll see how it goes. So yeah, right. It sounds like you have a really good picture of a tentative but really promising picture of how to understand what the rank of the Néron-Severi group of an abelian surface turns out to be in the general case, including the special cases. Okay, sorry, I just felt like saying that.
Well,
why are you moving around like that? It looks like you're looking for something.
Exactly. So this pen that I use for my tablet has mysteriously.
I thought you'd be very annoyed that I was rambling on saying nothing.
No, I was hoping you'd keep on doing it until I found this thing, but it's really irritating because.
All right, okay. Well, if I think of anything to ramble on about, I will. So let's see. You can always pause the recording.
I don't know how easy it is to pause the recording. Let me see if I can pause. Oh, I can. Okay. I'm going to pause the recording. I'll see you in a minute. Okay, I'm back, and I'm going to share my screen here.
Okay.
Okay.
I think I'm ready. Go ahead.
Yeah. So, right. So I want to talk about understanding this issue, that sort of the main issue that you raised. So I want to draw a diagram that has the issue in it. So it's part of the exponential sheaf sequence. So it's nothing new. We had gone through the exponential sheaf sequence last time, And well, unfortunately, this time I'm using my notation, which is sort of standard notation for it.
Sure, that's fine.
But only the little piece of it that's relevant for this question. And I'll be able to state the question once I draw this. So there's just 3 terms of it that are relevant here. So the first part is the connecting homomorphism,
Yes.
one of the connecting homomorphisms. And then the second part the second part is the coming from the inclusion of the sort of constant sheaf of integers into the sheaf of holomorphic functions, which people call O. So, okay, so this is the part that we need to think about. And so, so the image of the first arrow here, it's the Néron-Severi group.
I think I understand that.
Okay, so just to say it anyway, H2XZ classifies topological line bundles, complex line bundles on our abelian surface X. This other group classifies holomorphic line bundles on X. And we're just, the Néron-Severi group is just the topological line bundles that come from some or many holomorphic line bundles. So that's why it's the image. Okay, but then to like figure it out sort of concretely, and also to understand, to pose this puzzle that we were confronted with, we would need to think about the Néron-Severi group this other way, which is the kernel of the next map, which is just from the exactness.
Okay.
And so our puzzle has to do with like, what does the image of this next map actually look like? Because we have evidence that when the Néron-Severi group is small, and I guess you said rank less than 4, then its image in this thing, which is a complex vector space, may be something like a dense subgroup of that vector space, or at least like a non-lattice, a non-discrete subgroup of that vector space. So that's what we want to understand. But to understand it, we somehow need to understand the kernel, because the kernel is the Néron-Severi group. And so when the kernel of this second map is small compared to the overall codomain, then there's a lot of stuff that's getting packed into this vector space. And that's when we have this fear that the image is not a discrete subgroup. So we need to think about the kernel.
Yeah. Okay. So yeah, I agree with everything you said, but I can't help but being my eyes are gazing over towards the right one step, because that's where the effect of this proper dense thing might really kick in, right? What's that? That's the H2 of H2 with coefficients in O star. Is that right? Did I say that right?
Yep.
Because you've told me that has something to do with Zerbs or something like that, but also, right? I mean, it's looking like because of what's happening with the map on the right on the board, it's going to cause the next object to the right of that to look funny. maybe.
Yeah.
So I can't help thinking about that, even if that's not the main focus at the moment. We're trying to keep our eyes on this thing on the board. So go ahead.
Yeah. So I'm going to try to analyze this second map here. And so the way to do it, and that seems to be, so first of all, we use the fact that this coherent cohomology is isomorphic to the part of the Ram cohomology of our surface, and it's the purely holomorphic part. So I'm going to write, so the Ram cohomology I can just write as like cohomology with coefficients in C. The Ram cohomology is the same as the ordinary cohomology with coefficients in C, but then there's this Baez idea that you can split that up as a direct sum of pieces. And
yes,
and this is the piece which comes from differential forms that are differential two forms that are purely holomorphic.
Mhm.
Okay. And so then the way we take advantage of this is that the integral cohomology is it's mapped to the complex cohomology by change of coefficients. And this complex cohomology, this is the Ram cohomology. This is actually an inclusion for abelian varieties because there's no torsion. So this map in general kills off the torsion in the second cohomology, but there's no torsion for us. So this is just an inclusion.
Because of the fact that we're restricting to abelian surface case or something, is that right?
Yeah, that's right. Yeah. So I guess that's probably true. I mean, I know it's true for abelian varieties in general, but yeah, let's just talk about abelian
varieties. Okay.
So that's nice. So, and then the second, the de Rham cohomology, it's a direct sum of three pieces due to this Baez splitting. And well, maybe I'll just write it like this. P goes from 0 to 2, HP 2 minus P. This is like only slightly shorter than writing out all three summands by hand. So there's like this H20, this H11, and this H02. So it's like the holomorphic, the anti-holomorphic, and like the mixed holomorphic, anti-holomorphic part. And so then this thing, this direct sum, it projects down to, there's a projection down to the purely holomorphic part.
Trying to make sure I'm following this. So, can you repeat that last part again?
This de Rham cohomology projects down to the purely holomorphic part, which is one of the three summands.
Okay.
And so the key is that we've actually gotten something out of this, that this diagram here actually commutes, so that this map that we'd like to understand, you can think of it as two steps. One, a very bland step. We just change coefficients from Z to C. In this particular case, that means we're just like switching from a lattice, or switching from a free abelian group to a vector space that it's sitting inside as a lattice. Sorry, not as a lattice. Sorry. No, if it was like rank 2, whatever it was a rank something or other free abelian group. Now it's like a rank same thing vector space. So it's not like a full rank lattice. So we include into that vector space, and then the hard part is we got to figure out how this vector space splits up into these three pieces: the holomorphic, anti-holomorphic, and mixed part.
Yes.
That's where all the work lies.
Yes.
And then we project down to the purely holomorphic part. And that, and then we're done. That's so. Well, so notice, like, for one thing here, the kernel of this.
I'm just trying to figure out if you're saying something I've already known, or you're telling me something I haven't really thought about. It seems very,
I think you probably like almost knew it. We've said
there's something suspiciously magic about what you're saying, but go ahead. Yeah.
Yeah, it is magic. I mean, the magic. Yeah, it's true. There's magic, and there's like a non-trivial theorem that the coherent cohomology is this purely holomorphic cohomology, and there's like, well, there's a more trivial theorem that you can split up the Ram cohomology into these three pieces. So there's some work. But I mean, we've talked about these ideas, but we're sort of, but now we're like using them, and so yeah, so it's sort of magic. But the one thing is like so what we see is like the Néron-Severi group is the kernel of this top map here, but this top map here is an inclusion equal to an inclusion which has no kernel, followed by a projection. So all the kernel part, all the kerneling, all the kernel is going to be coming from this second map.
Well,
I mean, you
don't have to accommodate me, but I have a feeling that if what you're doing is just like sort of exploiting the Hodge diamond in a way, I might like to see a picture of how what you're doing relates to a Hodge diamond.
It's sort of, we have talked about it in those terms, and
okay, so on the very bottom you have like a whole row of the Hodge diamond. Yeah. Go ahead.
Yeah, I'll humor you.
I don't know if you were going to do this anyway, but go ahead. Yeah.
Nah, but I'll humor you. So
yes,
and
you can humor me if you want. Yeah.
So the Hodge diamond looks like this, and so
I believe that. Yes.
And so we're talking about this. We're talking about this second row here.
Yes.
And we've talked about it in these terms before. So the Hodge diamond is all about this complex vector space being split up as 1 + 4 + 1. But then sitting inside there is a
yes, okay.
Is a free abelian group.
Okay. So you're just reminding me, first of all, that the Hodge diamond is I should look at that as a diamond of complex vector spaces at this point.
Yeah,
and those are perhaps called, how did you pronounce it? Cohomology groups. Those
right.
Not nine whatever. Cohomology groups arranged in a square. Okay. And that 1, 4, 1 thing there, that's the whole. Yeah, that's the whole thing. I'm pointing to the screen, but nobody can see it. Right, it's the bottom, but right, the bottom H2XC. Yes. Okay.
Yeah, so we also know, and maybe I'll slow down and say it again or something, but we also know just from topology that this thing is we worked this out last time. This thing is a free abelian group on 6 generators. This
right. Okay. Yeah. I mean, I haven't thought about this in a while, and right, you reminded me of all sorts of things that have always confused. So right, it's yeah, I want to think that that 6 that you're describing where the cursor is right now is like almost the same thing as the 6 right below it, where we have 1 + 4 + 1 = 6. But there's a big difference because the one on top is integer and the one on the bottom is complex vector spaces, and that's where all the subtleties are.
Yeah, so I mean, so this map here is completely benign in the sense that this is a 6-dimensional a free abelian group of rank 6, and we're just complexifying it and getting a 6-dimensional vector space. So it's sort of like typically nice.
Okay.
The nasty part is that the way that this vector space splits up is not neat with respect to this 6 here. We've talked about that before. So
yes. But it's just really helping me to remind me of this. That yes. Okay. So we have like an orientation that causes problems between the lattice or this. I'm not sure lattice is exactly the right word, but this. This integer thing inside its complexification, and this thing. Well, I'm not sure whether I should really be thinking of a filtration or a grading, but either way, perhaps it's sort of it's potentially off kilter,
right,
in relation to the generating integers thing.
Right.
Okay. So I'm just trying to grok this. Okay. So yes.
So we want to get ourselves I want to get myself, I won't speak for you, in the computation, into the level of computational power where I can see the 6 generators of this free abelian group in some way, and then also see some basis for this 6-dimensional vector space here, but also see how they're a little, in general, they're sort of off kilter from each other, such that when we project down, there won't always be the image of this thing may not. So when we follow this through the whole process here, we're not necessarily going to get a rank 4 abelian subgroup mapped into here, but like it may have been off kilter. So we're just going to get like less of it actually makes it into this 4-dimensional vector space. So this is like the warm up, this general thing, and then the next step is to like actually get to know these maps better so that we can do stuff like that. And I've just begun the next step, but I think I know something about how I want to go about it. I always wish, like all mathematicians, that like the writing surface was infinite in size.
I mean, in my notebook, it is sort of infinite in size.
Yeah, my notebook, it is not. It only I can hop discretely to the next page. So maybe I will have to hop at some point. But let me just sort of say.
Okay.
So this integer cohomology. We can think of the cohomology of any sort of torus as an exterior algebra. And here we're thinking of it as like an integer exterior algebra. So we're thinking of this, we can think of, so here what I'm going to do is I'm going to pick a way to get my hands on this. I'm going to like have to pick a way to think of my abelian surface as a product of circles. And then
Okay.
this thing gets described as like an exterior algebra, and there'll be
Yes,
some,
yes.
yeah. So the first cohomology of a circle has this generator. I haven't made up names for these yet, but maybe I'll call these like E1, E2, E3, and E4. So those are the generators of the first cohomology.
Yes.
And so then this thing is like, oh, sorry, I don't know what your notation. It's like,
You can try. I can try to adapt whatever you like.
it's like, yeah. So it's like the integer span. That's the free abelian vector space on these guys.
Sure.
EI, EJ. So I don't know. Let me just write this thing for like span or something. I mean, it just means like the free abelian group on these 6 guys here. So that's fine and dandy.
I mean, sometimes I get worried about whether it's like a factor of 2 that we're dividing by somewhere, but maybe we're not. And I can always figure that out. I can worry about that later, but go ahead.
Yeah, we can, if we get that far, we'll be lucky. Yeah.
Okay.
So,
Okay.
Right. Hopefully it won't matter too much.
Right.
Because we're going to map them into this vector space here.
Yeah.
Well, it probably won't matter too much because we're mainly going to be thinking about like what's the kernel of a map. So if we like double everything, it's not going to.
Right. No
annihilate.
torsion to worry about.
Yeah. In fact, let me just write some stupid, I don't even know the usual notation for this. This doesn't mean like this is like the integer span of these guys.
Yes.
And so then there's this vector space here. The second cohomology with complex coefficients. Sorry, my computer is lagging.
Uh-huh. I can hear something lagging.
Okay. It's dangerous when you're working in a world of lagging.
Yes.
Okay, so there's this complex cohomology. And so here, that's just going to be like the complex vector space spanned by the same 6 guys. So that's,
Yeah.
so then, yes, the map from here to here is completely banal, or benign, or banal. So, okay, great. So, but then the problem or the interestingness happens when we start trying to think in terms of Debye cohomology.
Yes.
And so for that, we need to take this Durham cohomology and think about it in a potentially different way,
Okay.
And for that, we're going to need to think about, well, I don't know if we need to. Let's think about X as like C2 modulo some lattice.
Okay.
And that's nice now because then we have a nice way to think about the holomorphic structure, or the complex structure on X. And then that's going to be nice in terms of describing like these holomorphic and anti-holomorphic forms. So on X, we have these one forms, like DZ1, DZ2, dz1 bar and dz2 bar coming from the coordinates on C2.
Okay,
And so,
I think I'm following. Go ahead.
so in particular, this, well, I'm just going to sort of focus on this. Well, let's see, what am I going to focus on? Well, so I mean, we could figure out the different the different Debye cohomology groups that are in this they're in this sum here, are going to be built by like mixing and matching a certain number of DZs and a certain number of DZ bars. So like the purely holomorphic part is going to be this one-dimensional one in the Hodge diamond, and that's going to be the vector space spanned by DZ1 wedged DZ2.
I think I'm following, yeah.
Yeah. And then there's like the purely anti-holomorphic part, which is just all the bars.
Yeah, so that middle thing is mixing one with the other or something.
Yeah, so I sort of want to think about like, yes.
Yeah, okay.
I mean,
So it's mixing any one of the two on the left with any one of the unbarred ones,
right,
with any one of the barred ones. Okay.
Yeah, so we get 4 choices there. It's like 2 dinners and 2 desserts. So
yes.
Right. So, well, I guess what I write down now depends on whether I'm interested in like how much, what's the map all the way to the purely holomorphic part. That is, you know, this map here is mapping to the holomorphic part, or I could be interested in this other thing we've talked about, is like how much of the mixed part, the H11 part, how much of that 4-dimensional guy in the middle of the Hodge diamond do you actually hit? How much of this? So I don't know which one I want to focus on right now, but there's sort of like 2 aspects of the same thing,
Yeah.
but well, maybe I'll do H20. I mean, we could do either one. So the H20 of X, like you said, like we said, so that's like the complex span of the DZ1 and the DZ2, well, the DZ1 wedge DZ2. But
yes.
But we see that like the key issue is going to be how these generators that we're calling the E's, which coming from the different circles in our torus, are related to these coordinates, these Z's, because that's
yes, right.
Just like map these guys over to these guys and see what happens.
Right.
So,
yes. This makes me think like period matrix or something like that. But go ahead, yeah.
Yeah. So I mean, I'm not really ready to do any interesting case.
Yeah.
And maybe the boring case is like so obvious to you that you don't even want to see it. But I feel like doing a boring case.
Yeah, no, that's fine. The boring case, meaning in particular the one where the confusing things just won't happen at all. We're anticipating, we're expecting.
Yeah, I guess there are a number of those. There are a bunch of those cases like that have the property that nothing weird happens. But I'm going to pick like the most boring of all those cases, which is just the product of 2 Gaussian.
Sure.
Just to like warm up.
Sure. I mean, you know, it is true that when you pick a case like that, sometimes it's hard for me to see what's going on at all because everything is so boring. But nevertheless, let's try it.
Yeah. well, even that, even that is not, I mean, even then, it's not like the E's are exactly the same as these four guys. So you still have to think about it. And I figured like doing that case is like a good warm up to doing any interesting case, which I don't know if I want to try to do in real time or not. We could try or not, depending on how embarrassed we want.
I mean, are you really saying that it's not just the same, even in that vanilla case? I thought it might be the same, but you might have to, you know, you might have to agonize over whether E1 is.
I think let me try it. So we're going to do this case.
Okay.
Where, so we've got this abelian variety C2 model lattice, but this lattice is just Gaussian integers squared. So
yes.
So we could practically visualize it. It's, I mean, so the Gaussian elliptic curve is this guy with its edges identified. Square, that's supposed to be a square, and
so if I can visualize a regular tesseract, is that right?
Yeah, exactly. So this thing is like a product of two of these things with their edges identified. So I mean, this is like a metaphorical way to think about it, but it's not such a bad way to think about it.
Okay.
So this first one will have coordinates. This first complex plane, or the first square, will have coordinates I'll call like x1 and y1. So those are like the coordinates going along the directions that I'm marking here. The usual x and y coordinates on the plane.
Okay.
And then this other one will have to be like x2 and y2.
Okay, yeah.
And these, so now we had these guys called E1, E2, E3, and E4.
Yeah.
They were in like they were
right.
In the first cohomology of the.
I'm really suspecting you're going to be reteaching me here that complex differential geometry or something, where you have like, is that what we're going to do here? Those.
Yep, I guess. I don't know.
Something about bars and how, yeah, what are the bars on differentials or near differentials? What do those really mean? Okay, go ahead, yeah.
Yep, that's exactly it. So these guys get sent over to like de Rham cohomology. These integral cohomology classes get sent to de Rham classes. And those de Rham classes are just, I'll do it like this. It's like just like dx1, dy1. I mean, we have some choice here, I guess. Dx. Oh, sorry. This is probably, yeah. Okay. Dx2.
Sorry. How do you manage to make, you know, your tablet actually sounds like chalk on a chalkboard or something like that? How do you manage to do that?
You don't put it completely on your desk. You have it
right.
tilting off the edge. Okay.
Okay.
I don't, was that, you made it sound like it's a good thing, but.
Yeah, I mean, well, you could argue about it, but it's a good thing. But
more sensory input is good. Yeah. So what I'm doing is I'm saying that I'm taking I have this 4 torus, and I'm picking the 4 generators of first cohomology to be the ones that sort of wrap around the x direction, the first x direction, the first y direction, the second x direction, and then the second y direction. Yeah. So I mean, this is how the map goes. But then
Sorry, when you said this how the map goes, that means that those orders that you list things are,
Yeah, yeah.
Okay.
So
okay,
yeah,
that's fine.
all these four guys are getting mapped to all those four guys in
Okay.
order. But we had been working with these DZs and DZ bars.
Right.
And so, yeah, so probably maybe this is like what you were thinking about here. So each of these DZs, I is like 1 or 2. Maybe I'll call it J. There are 2 of them. Each of these DZs is going to be dx plus I dy. So that's that's just the rule. So it's just sort of motivated from the fact that the complex valued function z is the function x plus iy. It's a linear combination of 2 real functions.
I have the feeling that there are, really good motivations for this, but I don't want to figure them out right now. I'm willing to just sort of proceed.
Yeah, I think it's good. Yeah, okay, good. It's like, it's too late for that. It's like when you're taking a class and like the teacher's saying a bunch of crud and you're like, okay, I gotta understand that someday, but right now I just gotta take it. But it's not so horrible to think that dz is dx plus idy. Hopefully not. I don't. Hopefully.
Well, but there's some really good stories about this. But okay, but go ahead.
Okay, and then the dz bars. Well, it's like the same deal. It's minus. It's like the complex conjugate. I hear I'm like being very, and it just is because z bar as a complex function is x minus iy. But yeah, so the reason why I'm doing this is that like this is like the guidebook to see where these integral cohomology classes are going to go to in de Rham cohomology. When we think of de Rham cohomology in the sort of more Debye-ish way, where we're sort of preferring to use these Z and Z bar.
Yes.
So yeah, so speaking of like annoying 1/2s and things like that, you can see that like if I wanted to know what one of these dx's is.
Sure. There's a Hadamard transform there, sure.
Is that what it's called? Okay, that sounds so sophisticated, but okay, I guess it probably
certain people call it that, but go ahead, yeah.
So if I add these two, the y's cancel out and the x's stay there. So dxj is like 1/2. I don't really want to worry about these halves too much because I don't.
Sure.
I think that they're not like gonna kill us, but anyway, but
sure.
I mean, but the more important thing is that like it's like the same amount of z and z bar.
As what? The same amount as each other. Yes. Okay.
Yeah, and so like we can like begin to imagine like if we were dealing with a lattice that wasn't the Gaussian lattice, that like then something's got to change.
Yeah,
that's all I'm gonna say about that.
Okay.
But this is supposed to be like the vanilla case where we don't have to worry about that. And then let's see, even worse. So like to get the y's, you have to take this top one and subtract the bottom one. But there's this I here, so it's like 1/2i, and I didn't really leave myself enough room. I think my tablet's gonna not like this. That's an I. Gross. So dz j minus dz bar j. So right. So let me maybe now jump to the next page. And so what I'm going to try, it's always bad to do a calculation right when you're jumping to the next page, but I'm going to say like which these 4 guys go to, what they get mapped to. But in terms of this Z stuff and the Z bar stuff. Maybe I'll do one out loud. So like E1 is getting mapped to DX1, but that's like 1/2 of this DZ and DZ bar 1. DZ1 plus DZ1 bar.
Yes.
And then this one will have this minus sign. Let's see if I can do it. Let's see if I can
Okay.
do it. So our map is like E1, E2, E3, E4 are getting mapped to D1/2 DZ1 plus DZ1 bar. This one's getting mapped to 1/2 DZ2 plus DZ2 bar. And this one's getting mapped to 1/2I DZ1 minus DZ1 bar. And this one's getting mapped to 1/2I DZ2 minus DZ2 bar. Okay, so now,
I mean, I think I'm, so to speak, following this, unquote, at the level of just, calculation by hand or something. I can't, I'm not really visualizing too much at this point. Go ahead, yes?
yeah. Yeah, well, yeah, it's a little harder to visualize these complex differential forms.
Sure, sure.
So that's all I'm doing, basically,
Sure.
either. So now remember what we were up to once upon a time. So we had this integral cohomology, but now second cohomology. So it's like,
yes,
the free abelian group on these 6 generators that are the wedges of 2 of these guys.
yes,
And then we have this, well, this whole big vector space here would be 6-dimensional, but it's split up into parts. And for example, the 2,0 part would be this part with just Z's. So what we're trying to do, I guess, well, I think maybe, I mean, it's possible that what we are we trying to do? I guess one thing we're trying to do is like understand the image of this map and let's try to show that it's like not some crazy, wild, dense thing, but just something very nice in this case, the 4-dimensional free abelian group. So if that's what we're trying to do, then we're trying to see, we're going to follow it around this way here. And so we're going to try to see, we'll take the integer cohomology and then we'll like see how much of it, so to speak, lands in this H20 part.
Yes.
Which, let's see, is that what we're trying to do? Yeah, that's what we're trying to do. Let's see, is that what we're trying to do? So this is just a, so this is just a 1-dimensional complex vector space.
Right.
And so we're trying to show that they're like not a whole lot of we want to show that that's not, that the image of this map is not dense in that 1-dimensional complex vector space. It's just a discrete abelian group. I guess they're theoretically they're different choices. The choices there are that it could be like a rank 0, 1, or 2 abelian group.
Depending on what?
Well, depending on what abelian variety we'd taken.
Okay.
We've taken a specific one, but So, okay, that's sort of what we were trying to do with this stuff. So
Could you just go back for a second? Because I am trying to, the previous screen. Is this where you just were? Oh, this is just where you
the very first page, so to speak.
So, okay, sorry, something's confusing me. I'm trying to catch up here. So we are focusing on, as you say, this most vanilla case where it's the Gaussian thing in both factors. And I'm trying to cheat a little bit here and, you know, anticipate what's going on. Maybe I shouldn't be cheating, but I'm cheating because I'm a little bit worried that I'm not seeing it work out the way I was expecting. So let's see. So the H2 of X with coefficients in Z, that's this 6-dimensional thing, right? Rank 6.
Yep. That.
Okay. And then right to the right of that, there's this 1-dimensional complex vector space. Is that right?
Yep.
So rank 6, rank 6 over the integers, going to dimension 1 over the complex numbers. And we're doing it in this particular case. Sorry, how's it going to work out? It's going to work out that it's going to have like it's going to have a lattice, a rank 2 lattice as image.
I mean, I guess we should like admit that we're actually like finally figuring it out, but
okay, yeah, maybe I shouldn't be cheating, but I was just getting confused.
Well, I'll cheat in this insofar as like last time we met, we like did a optimistic guess of how it worked in the nice case.
Yes.
And that was based on certain optimism, and that did that optimistic guess indeed was suggesting that the image here is a rank 2 free abelian group. So it's like a lattice in here. Yeah.
So that.
But this is, by the way, why I said, like, in theory, the image of this thing, if we accept that it's not dusty,
yes,
it could in theory be like a rank 0, a rank 1, or a rank 2.
Yes.
Abelian group. And so just like to keep the suspense going a little bit, I mean, we have to like make sure that there's like, it's not one of those other cases.
Yes.
Maybe you are even beginning to start getting actual suspense where you start.
Well,
it's good.
I'm just vaguely recalling certain numerology that we did, and I'm not recognizing that numerology showing up here yet. But
yeah, the numerology was that this thing was.
I mean, maybe the problem is that at some point I was, really focusing on the idea that people had sort of hinted to us that in the really generic case, you just get rank 1 Néron-Severi. And maybe what's burned into my mind is what happens if you make that assumption. And that's why I'm not recognizing what's going on here yet.
Okay. You had, in the notes that I copied down, you started by doing the super nice
yes
case, the super non-generic case. And that's, yeah, so this is that, yeah. So I'm staring at my paper notes here and seeing.
Yes. Okay, maybe the best way for me to cheat is to go back, as you're talking, I'm going to go back and look at the notes from last time. I think that's what I'm going to try to do.
If you want to share them, it's fine. I mean, I don't mind taking them.
Well, they might just be too messy or something. Let's see.
I saw something pretty nice where you like, I mean, I'll just tell you, like this H2 you wrote is like, or maybe I just wrote it. It's like Z4 plus Z2 equals Z6.
Say it again.
You gotta look at what I'm pointing at, though, or one.
Oh, right.
So in my notes, you said like this is Z6.
Yes, Z6. Yes.
This thing you wrote is like R2.
Yes, I did. That's right.
And so we were like imagining that this Z6 split in the most beautiful way is like Z4 plus Z2.
Right. Okay. Yeah. I'm just doing a really bad job here of keeping up with everything that's going on. But yes, I can see that this does match the notes from last time. So okay. I'll just try to follow along. Keep going.
Yeah, and I think we'll see it all. That is, I think it's going to work, and I think all that stuff is really going to be borne out. Well, so maybe just to like maybe just not to like really.
Okay. Sorry. So let me just. I'm still struggling to catch everything. I'm just trying to say out loud what I thought was going on. That the good thing about the vanilla case is that the rank 4 is so high that it kills off a lot of the 6 and gets you down to just 2, and that can fit into the complex numbers. Rank 2 Abelian group can fit into the complex numbers, no crowding. So okay, so then when we eventually get into more tricky cases, what's gonna happen is that rank 4 is going to start going down, and it's going to have less of an ability to kill off a lot of the 6. And that's, so a big remainder of the 6 is going to try to squeeze into the complex numbers. And sorry, I'm just orienting myself to try to what was the general drift of things. Sorry. I'm okay. I should really shut up and try to follow along what you're saying now. Go ahead. Yeah.
Okay, let's try to do it. So these were the generators of first cohomology and what they get mapped to.
Yes.
And then, so our goal here is to think about the generators of second cohomology, which will be these wedge. This is some kind of, I'm using wedge product for like wedge product in integer cohomology. Some idiots use cup product for that, but anyway. And so we want to see what they.
Sorry. I'm interrupting. Can you just go back to the previous screen? Just let me stare at the screen, the other one. Okay. The other one. Let me stare at your other screen to see if I'm really following it. Because I think part of the problem is I'm just, I'm used to drawing the long exact sequence split up into rows with the connecting homomorphism actually jumping from one row to the next. Yeah, and and I'm just trying to orient. Okay, so let me see if I understand what you're saying. So there's the connecting homomorphism. That's the beginning of the row there, and that is going to. Why is that still confusing me? Okay, let's see. So there, okay, the connect, right, okay. So it's the connecting homomorphism that is really important there. Okay, so, yeah, I was just staring at the picture wrong. I was like off by one arrow and it was confusing the hell out of me. Okay, so that connecting homomorphism is really important.
I mean, so it's images the Néron-Severi group, but it seems that when push comes to shove, it's easier for me to think of the Néron-Severi group as the kernel of the next one. Because the connecting homomorphisms involving going from 1 to 2, it's a little bit slippery, whereas staying in degree 2, it's pretty nice. This is my hope that the integer cohomology H2 we can understand using wedge products of integral cohomology generators, and then this H2 with coefficient, this coherent H2 we can understand using wedge products of DZs, and so hopefully that'll make it easier to understand the stuff like the kernel of this.
Yeah. I think I was just making a stupid intuition mistake. You've drawn this picture with 2 different ways of thinking of the Néron-Severi group. as an image and as a kernel. And I think I was just thinking about the wrong way. When you were talking about thinking of it as a kernel, I was still staring at the image, or vice versa, or something like that. Okay, so I think I'm catching up here. Okay, so sorry, that was an interruption to.
Yeah, no, it's okay. I mean, I've been spending my hours doing exactly this type
Sure.
stuff. So like the actual calculation part of the calculation is not incredibly hard, but like from figuring out what, just like remembering what
Yes.
is going on, take some time. Well, let's see. I think it's maybe the right way to do it is to just like do some examples. So that is, I'm gonna do something like, so remember what we're trying to, let's see, so what are we trying to do? I'm gonna try to think about the image of this map. That's what I'm gonna do.
Yes.
So I'm gonna try to. So I'm gonna try to build things that are just built up out of DZs and not DZ bars.
Yes.
And out of things that are in the image of this map. So in other words, like I've got this map here that's sending E1, E2, E3, E4 to various blends of DZs and DZ bars. And I'm ultimately shooting to get a hold of things that are just built up out of DZs. But let me just try to like do one. So like suppose I do like E1 wedge E2. So then I'm wedging this stuff with this stuff. So there's this coefficient that I don't probably really care about too much. And then I get something like, well, okay, I'll write it down. DZ1 wedge DZ1. Well, that's to 0. Plus, I'll do DZ1. I don't know why I'm doing it in this order. DZ1 bar, wedge DZ1. Then we get some stuff with minus signs in it. Minus DZ1, wedge DZ1 bar. And then stuff with only, with a plus sign. And with another minus sign. Minus DZ1 bar wedge DZ1. Okay, so sorry, I think I did something stupid. Sorry, DZ1 bar. Okay, you're too easily here. So I get these 4 things, but the ones with the wedge product of a 1 form with itself is 0. So some of the stuff goes away.
So the middle stuff hangs around.
Yeah, so that's gone. That's gone. This hangs around. The wedge product is skew symmetric. So that stuff is really just one thing. And so, sorry, I wish this page was bigger, but anyway, so these 2 are equal. And it doesn't probably really matter, but that means like we get this 4 turns into a 2 here. So I get the DZ1 bar, wedge DZ1. Well, that wasn't so hot.
Wasn't so what?
That wasn't so good, because we're aiming to get things, well, it might eventually be good, but we're
Yeah.
aiming for things that are just like built up out of DZs. So if we thought about it harder,
Right. Okay. Yeah.
yeah. So if I had thought about it harder, the only thing with, I mean, the thing we're really shooting for is things that look like DZ1 wedge DZ2. So we got to like mix some Z1s and some Z2s. So this particular one here was.
But is it possible that you just said it wasn't so hot, but in a way that actually might be a good sign? I mean, right, the danger is of the image becoming too big, and you're just sort of giving propaganda. I'm just guessing.
Yeah,
but you're giving propaganda for the idea that in this case, the image isn't going to be excessively. This is the rare case where the image is not going to be that big.
Yeah, and I keep vacillating in my mind between whether I'm really wanting to be focusing on the image of this map, or whether I want to mainly be thinking about the kernel of this map. The kernel is the Néron-Severi group, after all. And one thing we could try to verify, for example, is that kernel has rank 4, which is what we're expecting. So it's not. So in fact, we found something just now that was in the kernel. We found that this thing gives a DZ1 bar wedge DZ1, and when you project that down to the purely holomorphic part, it just gets killed because it's not.
That's right. So you were being wrong-headed by thinking that it was bad news to get something in the image. It's actually good news to get something in the kernel. Is that right?
I was trying to find things that would.
I mean, good news for now that we're trying to, we're trying to get things to work out the sort of good way. Later on, we're going to try to get things to work out the ugly way.
Yeah, well, they're both, yeah. So this thing gets mapped to here. I'm afraid I'm just going to erase this calculation.
You do erase too many things for my taste, but you don't have an infinite whiteboard.
Yeah, that's the problem. I mean, I have an infinite whiteboard, but then because it's on separate pages, I have to keep copying things over. Maybe I won't erase it. Maybe you've convinced me not to erase it. It is all recorded, but that's sort of different.
Right. Yeah, no, that's a good point. It's all recorded.
Let me just. Well, so I mean, since we were able to get DZ1 bar wedge DZ1, we're going to be able to get DZ2 bar wedge DZ2. There's no difference between the ones and
I think that's right. In this situation, I don't see any difference. Yeah.
Yeah. So we'll get those. And right. Oh yeah. We'll get those. But notice, by the way, one thing is that like you might look at this calculation and you say, oh, good, we got DZ1 bar wedge DZ1. So we like get the whole vector space spanned by that. But that's not really right way to think, because we're interested in mapping this free abelian group into that. So like we might get this thing in the image of that free abelian group, but not get the thing with the eye not there.
Yeah.
So actually we have to pay, I mean, it depends how accurately we want to pursue this, but
yes.
Yeah, but it does matter, because I mean, we're hoping that like a rank 4 abelian subgroup of this thing gets killed. And so we found one possible generator of that rank 4 thing, but we might be hoping to get like, well, we hope to get 3 more. So we like, it would be really good to get like the same kind of thing, but without the I in there. That would like count as like a different generator. So I guess all these niggly details like actually matter. Right. Let's see. So
let's see. Okay.
This is annoying.
The
this requires like lots of paper.
yes.
Or else lots of hopping back and forth.
Yes. I'm trying to fix all my mental typos as we're going along. Go ahead, yeah?
Let me do some stuff here. So I just did E1 wedge E2. I'm just going to take the low road and we're going to do E3 wedge E4, which is like just the same, but with these Z2s instead of the Z1s.
Yep.
So I'll just do that. So okay. Then I've got to start doing something more interesting. And like a different kind of thing would happen if I did like an E1 wedge E3. So like mixing up some Z1s and some Z2s. I think I am gonna erase some stuff. I'm gonna like eliminate the calculation and so that I have room to do another calculation while I'm staring at the at my guide.
Yes.
So what I want to do next is like see what kind of stuff happens when we do like E1 wedge E3.
Sure.
So it's like 1/4 DZ1 plus DZ1 bar wedge DZ2 plus DZ2 bar. Okay. So this is sort of this one doesn't have so much stuff canceling out.
Right. That sounds
So
right.
like I get DZ1 wedge DZ2. But then also get like DZ1 bar wedge DZ2 bar. This is sort of annoying. That is, we may have to take like lots of linear combinations of these things that we're getting here to like get the stuff we really want. It's like either purely in the kernel or not killed at all. Then we get these, oh wow, we get 2 different cross terms. Okay, so every single term is like its own thing. Okay, so this is just a stupid thing to write in a way. I'm not really this expansion process is not especially enlightening because I'm just getting 4 terms that don't cancel or anything. Sorry, and I also I'm running out of room.
Right.
I'll get rid of that. So it's possible that like at some point around now or soon, I'm gonna just like
Sure,
give up and say that this is like a thing that's better for me to do
sure.
uh, on my own. So yeah, but at least what I know is that like I can go, I have the ability to go ahead and do this and,
Yes, yes,
get it done.
sure.
And so, I mean, so you can see here, like I've got this thing that I want, so to speak, this thing that's like not getting killed off at all. DZ1 wedge DZ2. That was supposed to be the one of the, that was supposed to be a guy that's like in the image of this, that persists into the image of this map here. It's sort of the opposite of them.
Right, okay, right.
I'll sort of keep flip-flopping between deciding whether I'm thinking about the kernel or the image, which is sort of disorienting, but.
Right, I think I keep on falling into that trap. Right, so, right, every time we find anything with bars in it, you can say that that's irrelevant for the image.
Oh, well,
Yeah.
actually, that's a good point here. So we got this big thing here. Yeah, that's a really good point. So we've got this thing here, but then we couldn't map it if we want, and that's great. Oh, why didn't I think of that? Okay, so we got this element of de Rham cohomology. There's like a mix of DZs and DZ bars, but we can go ahead and say like, oh, let's just map it down to the purely holomorphic part. And that just means throwing out all the.
I think that's right.
Yeah, that it is a very clean projection kind of thing.
Yes.
And so that will give us a guy in the image. And that actually makes me extremely happy now that I think about it, because so this thing like projects down to just the DZ1 and DZ2 part. Yeah, so that's actually.
Yeah, I think that's right. I think that's right. I mean, I'm still catching up, but I think that's looking promising.
So
And
that's
the previous and the yeah, okay. Okay.
So that's really nice. And basically, to get the image to be at least as big as we expect it to be, we just need this guy and then like another guy that looks like this guy but has an eye in it.
And you think that's going to be E2 wedge E4 or something?
Yeah, yeah. Or probably there'll probably like two that will will do that. But E2 wedge E, yeah, so E2 wedge E4 will definitely do it. Now we can do them much faster. Yeah, so we see a DZ1 and a DZ2 there. Oh wait, no, you picked the wrong. You picked the wrong one.
I picked the wrong one?
Yeah, because there's an eye here and also an eye there. So you overdid it on the eyes.
You want E1 and E4 or something? What do you want?
Something else. We just, yeah, what did we do? We did E1 and E3, but E1 and E4 would also work. E2 and E3 would also work. It's okay if multiple guys get mapped to the same thing in the.
Oh, right. I forgot that like the only thing that's different here is the reals versus the imaginaries in the.
Yeah. So okay. So
complex vector space. Yeah.
So the image is including the thing we just saw. 1/4 DZ1 wedge DZ2 after we project down like that. But we could do like, yeah, we could do like, we could do like, sorry, we could do like E2 wedge E3, these two guys. So we get like 1/2I, sorry, 1/4I.
Yeah.
DZ1 wedge DZ2. Or we could do E3 wedge E4. Whoops, no, never mind. That doesn't, no, that I can't do that. That is just Z2s. That
Okay.
so, but but anyway, that's,
Right.
we've sort of seen that, like, that's all the image is we've seen the images contains, we've seen that the image contains 1/4 dz1 wedge dz2, and we've seen that it contains 1/4 dz1 wedge dz2.
Yeah, I mean, I'm trying to check that there isn't anything else that's gonna, give anything dense or anything. I'm trying to make sure that it's discrete. So
Right. Yeah. So we just have to check that there's like nothing else.
I don't think there's anything else, but yeah.
Yeah, I don't think there's anything else. If we wedge two guys with DZ2s in them, we don't get nothing. If we wedge two guys with DZ1s in them, we get nothing. So it's sort of only the cross terms that
Yes.
can show up, and there's sort of this cross term, this cross term,
Yes.
this cross term, and this cross term. But the only things you get from any of those are these two kinds. So so maybe just sorry, let me just write down something. So like we have the image of this map from H2 XZ to going all the way to H20 XC, and that's this coherent cohomology. This thing here is equal to like the integer span of 1/4 dz1 wedge dz2 and 1/4I dz1 wedge dz2. So
see,
okay,
to me,
well,
go ahead.
I'll count that as I'll count that as a success and not try to be hard about the kernel.
Of course. It's just, but it's in fact, it's. I mean, I'm right. I'm a little bit impressed now, if I'm not misinterpreting. A little bit impressed. I mean, that you seem to have done this calculation in a sort of first principles brute force way almost. And now I'm imagining that you could use the same method, maybe with the Gaussian times the Eisenstein thing, and maybe we would actually see in that example getting this non-discrete image. I mean, I'm not requesting you to do that right this second, but I'm just idly imagining that it might work out that way.
Yeah, it might work out. So we can like stare at it a little bit. So like one of these squares would get slanted.
Yes.
And these, like we could leave the horizontal direction alone and just like slant things. And so then this thing that was called Y1 would now become this sort of thing that shows up when you got like a cube root of unity. So it'd be it would be like 1/2 x1 plus square root of 3/2 y1.
Something very much like that, yeah.
And then not do it over here.
Right.
And yeah, so that's like so in fact that's like not a,
so for some reason I can't see the time. What time is it right now?
It's 10:03. So we used up a bunch of time, but
10 in my time zone, that's
sorry. It's 20 minutes till
20 minutes till, yeah, okay. Until the sheet quit.
So this is enough of this stuff, and I'm happy.
That's enough of the stuff, but if you have 20 minutes left, like you could try the next calculation. Or do you have something else you want to do right now? Or do you want to quit right now? Or do you?
No, I don't want to quit.
Yes.
But I don't feel like doing this.
Okay, sure.
Next calculation, because it's going to be, then I'm going to really want to have like a nice big piece of paper.
Okay, but you did encourage me to think that even I might be able to do this calculation. Okay.
Yeah.
Okay, so where are you going next? Yeah.
Okay, so if you're willing to have like another episode, so to speak.
Yes.
Um,
Or, if I don't want to,
I think I have
whichever,
like
if you want to say more about this, that's fine too. Just go ahead.
no, I do. Yeah, no, this is all I have about exactly this.
Sure, sure.
So the other thing I was doing,
Yes.
yeah, I think this is like really. Let's see, I think.
See, I really, this wasn't the way I was expecting you to approach this, I don't think.
Uh-huh.
Like I say, you almost did it like from first principles or something. And I'm not sure what I was expecting, but
I just don't have enough other tricks up my sleeve
yeah.
to know how to. Well.
Okay, well, yeah, we'll see how it goes. Keep going, yeah.
Yeah, so I can say it this way, that, what I do know is other ways of thinking about the Néron-Severi group.
Yes.
One thing I want to know is like, how are all those different ways connected to each other to really
Sure.
But none of those other ways instantly helps me figure out the map from the Néron-Severi group. Sorry, none of those ways instantly helps me understand the image of this map that or kernel of this map that we were trying to understand from the second integer cohomology to the coherent cohomology. So so the coherent cohomology was like what was bugging me. The coherent cohomology is still bugging me, by the way, because like for the other two columns in the long exact sheaf sequence, we've got these sort of nice conceptual interpretations of like line bundles and holomorphic line bundles.
Well, there's some really interesting, simple-minded discussion of the semi-conceptual interpretation of this coherent cohomology, or whatever we're calling it, in like the Wikipedia article on, what is it, cohomology of coherent sheaves or something like that.
Okay, well, I'll have
I probably don't have anything to say about this, but it is interesting to read what they say about it. And partially because they give, a very interesting history of it.
Yeah, okay, well, I'd like to understand it. So right now, my main way of understanding it is just that it's this pure, that is like to understand it. They're like abstract ways to understand sheaf cohomology, but the main way where I can like really get my hands on it is this interpretation is like the purely holomorphic part of the de Rham cohomology. But that somehow.
Well, the impression I got from Wikipedia, don't trust me on this, but the impression I got from Wikipedia is that in some sense, the coherent cohomology is measuring the non-affineness of the variety.
Oh, okay. Okay, in the sense of like that sounds conceptual.
Right. Right. Potentially, if I'm understanding it correctly. Right. Like cohomology. Right. Sometimes people say that cohomology is representing the deviation of something from something, and in this case, it may be the deviation of the variety from being an affine variety. I'm not sure I said that exactly right, but that's the vague impression I got from the last time that I read the Wikipedia article on it.
Okay. Yeah. You've talked ages ago about like how there's always something mildly
let me try to make
unsatisfactory about describing some quantity deviation from something being true.
Sure. But let me try to make it a little bit more precise what I say. So what do we mean by measuring the deviation? What happens in the case where there's no deviation? So I think what happens in the case where there's no deviation is that, the cohomology is just really the same as the coefficients. That's the kind of what we mean when we say that there's no deviation, right? There's no. So all you're getting is everything is just the zeroth cohomology, and the zeroth cohomology is the coefficients. And that's, that's the no deviation phase. And then, when you're studying these projective varieties, you're definitely getting something that's non-affine. So anyway, that's my vague idea. Sorry, go ahead.
Okay. Right. Let's. So the more we talk about other things, the less I remember what I was going to say.
Sure,
So,
sorry for the interruptions, but it's a trade-off.
yeah. Right. So I want to, yeah. So these are like two other ways of thinking about the Néron-Severi group that I wrote about on the N Category Cafe, and
Yes.
they may seem very familiar to you, or they may not quite.
Yes. Yes.
So one of them is this. So okay, so here I'm being sort of general. So X is like any abelian variety, and so it's like some complex vector space modulo some lattice V mod L. And so one way to think about.
See, now I think you really are veering towards the Jordan cone stuff, secretly or not so secretly.
Oh yeah, I'm trying to get to the Jordan stuff. Yeah.
Okay.
Yeah.
Go ahead.
So I am. So one way, okay, in fact, I'll try to like do it fairly fast. Okay, so well, there's like two ways. Well, okay, I've got enough time. So there are two ways to describe it, and we've sort of like almost talked about this stuff, but I'm not sure we ever did, and I think I didn't understand it so well back then. So
I halfway understood it. Go ahead. Yeah.
Okay, so maybe I understood it, but
I halfway understood it because I was really trying to reinvent it myself, so that forced me to understand something about what's going on. So go ahead.
So one way to think about the Néron-Severi group is that it's alternating maps from V times V to the reals, but such that they get along with the complex structure.
Yeah, to me, this has, when you really take this definition apart, it's really, really directly telling a story about taking a topological line bundle and then getting it to become holomorphic. That first thing you're writing down, the A itself, that's the description
so
of
you're making me want to like make it more beautiful in the way that you're describing. So there are two conditions that
this is the part where I was threatening to slow you down and interrupt you because.
Well, you are.
Okay, go ahead.
So the one, okay, so the first condition is that on the lattice it takes integer values. So that would be just
yes.
That's just the topological line bundle classification there.
Yes.
I mean, and this is sort of redundant in a way, but
there's a whole long story about this, but it makes a lot of sense that this is a 2 cocycle, an integer 2 cocycle on a torus.
Okay. So this one you understand so well that you can't resist.
That's right.
Explaining it, which is fine. That's good. So that's number one, and then another one.
Somehow that thing that you wrote at the bottom, somehow, if I stare at that long enough, that's going to tell me that we've got this holomorphic structure. We're supplying this holomorphic structure. Yeah. Okay. Go ahead.
Yeah. So then there's this other one, which is sort of getting closer to stuff about Jordan algebras, which you can you did explain all this stuff. So we can also think of them as hermitian guys.
Yeah.
From V times V to C. So hermitian means something. Hermitian has some meaning to such.
I'm not sure that it's that different from any standard meaning, but go ahead. Yeah.
Yeah. Well, yeah, we don't want it to be positive definite. That's
okay.
We want it to be definite or even positive definite.
Fair enough.
Somehow, until I was ever getting into this game, I always thought it was positive, that hermitian meant that. But
I don't know. Never trust me on terminology.
Yeah, well, no, it's not a matter of you. I think it's actually people just
sure
differently in this gang.
Sure. At some point here, we're supposed to say Riemann form or something like that, but
yep,
not sure exactly where.
Okay, so this is like the second.
And for a lot of people, this is just like an automatic algebraic equivalence or something like that between all these different things.
Yeah. So, okay, so I want to think about it the second way.
Yeah.
And then I want to tell you about the Rosati involution and the Jordan algebra structure?
Yes. Sorry, I have to know. And I mean, you're saying hermitian thing here, that's unitary. I mean, there's a lot of, this is where my attempted Minkowski 3+1 space tries to kick in here. And, I'm trying to interpret all this Rosati involution in terms of what am I saying? I mean, an involution is really a way of encoding a hermitian structure or something like that. Encoding a unitary structure or possibly a degenerate unitary structure. Let's see, what am I trying to say? Well, okay, maybe I should let you go. Go ahead.
Yeah, I'm not going to mainly, I guess I'm not mainly going to talk about the Rosati involution because the hermitianness is the condition of being the fixed point of an involution, an anti-involution. And so it's sort of been like absorbed into here. So I mean, I could like cross out hermitian and I'd get something.
Yeah, I guess part of the point I was trying to make here is that all this, there's a whole lot of geometry going on here where the lattice can be thought of as an afterthought. So I mean, right? I mean, this involution, it should have an interpretation in terms of this unitary or perhaps pseudo-unitary structure on this space-time, this 3+1 thing. Right? I mean, the lattice and the ring, the discrete ring inside the continuous thing, the discrete lattice inside the continuous thing, these are just afterthoughts, the way I'm thinking of it. The actual anti-involution can be thought of without thinking in terms of the discrete structure at all. I think that's the intuition that I'm trying to use in understanding this. But again,
Yeah,
sorry, that's an interruption. Go ahead.
But that's actually very right for what we're doing. In fact,
yeah.
When, for example, a lot of times what people do, because it's relevant, that's the way to think for what we're doing now. Let me just put it that way.
Okay.
So,
particularly for the abelian surface case, because it's very fun in that case.
Yeah, but in fact, for any case,
yes.
So it's nice to. So in fact, that's what I'll sort of do. I'll mainly think about these hermitian structures on the complex vector space. And then
I mean, in the abelian surface case, I can get away with pretending that I'm just doing special relativity. Whereas in the general case, I would have to be doing quantum mechanics.
Yep.
Okay.
So
serious Jordan cones instead of just light cones.
Yeah.
Yes.
Okay. But I want to get to the Jordan algebra structure. So
okay.
So here we go. So I'm going to take the Néron-Severi group, and I'm just gonna write it down again. So it's these hermitian guys. That are have this integrality condition, but I'm not gonna do a lot about the integrality condition. That is gonna play a sort of secondary role in what I'm about to say. And what I'm gonna say is,
it certainly does kick in at some point, but you can start out ignoring it a little bit.
So what I'm gonna say is not like, so what we're gonna do is like pick, well, the way they say it is like pick a polarization. So what picking a polarization means is it's going to be picking one of these guys in the Néron-Severi group, but actually like picking one that with some special property that the hermitian guy is like positive definite. So it's just a positive definite H.
Again, my vague intuition about this is that it's like turning the space-time into a space.
Yes. So, okay. Now
which means the Jordan cone is turning into an actual Jordan algebra with a unit.
Yeah.
Okay.
I told you that I'm going to describe the Jordan algebra structure. Yeah.
Okay. When the Jordan, I may just,
If I don't talk fast enough, you're going to just like tell. tell it to me and say like, I don't even get any credit for steering the conversation in the direction where you, yeah.
Oh,
so-
you're definitely, I'm definitely following, I'm not leading here. You might,
Okay.
I'm just,
Okay. So we're going to pick one of these guys that's positive definite, one of these Hermitian forms H, and
Yes.
then the standard trick is that any other one has a nice description in terms of this one. Any other guy like H prime, you can write out in this sort of usual way. So like H prime is some other Hermitian form. And you can write it in terms of a single definite Hermitian form by sticking a linear operator in there.
I mean, I was about to ask, where is a boost here? Are you telling me A is this boost or something like that?
Well, I don't want it to, I don't.
Okay, we don't have to worry about that, but it's just,
Yeah, I don't think of it as a boost, but it's a linear operator from V to V, and it's reason why.
I mean, it would only be a boost in the surface case, really. But go ahead, yeah.
But the main thing is that this A here has got to be self-adjoint for the H prime to be Hermitian. So like multiplying by 2 would be like a great example of an.
Yeah, that doesn't sound like a boost. Must be some related operator. But go ahead, yeah.
So there's this thing, that like you can describe. People often describe Hermitian forms as self-adjoint matrices, but they do that if they have like a background Hermitian form.
Sure.
So that's what we're doing here.
Sure.
So then, okay, so once we've picked this, so now, right, so now that we've picked this polarization, we're able to think of elements of the Néron-Severi group as particular. I mean, there's some extra integrality condition that I'm not talking about, but we can think of them as self-adjoint operators on our vector space. And so then the Jordan product is just like the usual Jordan product. But like the good way to think about it, the good way to think about the Jordan product sometimes is to think of think of it in this, not in like the usual way of a Jordan product, but think of it as like this quadratic Jordan algebra thing where you.
Yes.
Or like if you give me.
Yeah. Well, go ahead.
So if you give me 2 guys, and I'm going to say it the way I want to say it. If you give me 2 guys in the Néron-Severi group.
I mean, there's another multiple meaning of polarization going on here, but go ahead. Yes. Like polarizing a quadratic form or something, but go ahead.
So if you give me 2 guys in the Néron-Severi group.
Yeah.
H prime and H double prime.
Yeah.
So they're going to correspond to 2 different self-adjoint operators, A.
Yes.
Sorry, this. Let me call this A prime and A double prime, and you can compose. You can. Sorry. No, I'm not saying it right. Darn it! I'm blowing it at the crucial moment. Let me say it in a very geometrical way.
Okay.
So
that might be better. Go ahead. Yeah.
So what we're doing here is we're saying that I can get any element of the Néron-Severi group from my polarization by this kind of self-adjoint stretching, squashing process.
Yeah, I mean, there's a, what is it called? A Hermitian symmetric space of these Hermitian forms or something like that? I don't know.
Yeah. But so the way I want to think about it, right, is that these Hermitian forms, what they really wind up meaning is the Kähler structures on the abelian variety. I mean, the tangent space of there's like translation invariant Kähler structures on the abelian variety, which is the same thing as like Hermitian forms on this tangent space, which is this vector space V. So the
Yes,
idea,
which I can also just picture as the universal couple.
yeah. So the way to think about it is that like we've picked the polarization, so we like pick the Kähler structure on the torus, and then we can get all the other Kähler structures by stretching, squashing the given Kähler structure using one of these self-adjoint operators. And so that
I mean,
means,
I mean, again, these are like unitary or Hermitian rather than just quadratic. But there must be some sort of ellipsoid-like visualization of these self-adjoint things.
yeah, there is. They have to have the I mean, it's because they're Hermitian rather than just like orthogonal structures, they have to have some like compatibility with multiplication by I, but they're like,
right. Okay, so there's some special ellipsoids of some
yeah, they're
kind.
ellipsoids that are preserved by multiplication by I.
That sounds right. That sounds right. That sounds right. Yeah.
Okay, so
I mean, if you're trying to describe this geometrically, then that helps.
I really am, and
yeah.
and so yeah, in some ways I should like give up on the formulas and sort of, so it's sort of like we've taken our polarization, we say like, okay, that's our standard Kähler structure. So I might as well just draw a picture in the tangent space where it just looks, where that ellipsoid is round. This is like a rosy picture because if this is like really a two-dimensional real picture, then multiplication by I preserving it means that the only decent ones are round, which is like why elliptic curves don't have an interesting supply of truly different polarizations. But I'm gonna draw that in a picture where I'm gonna like draw ellipsoids of different shapes. So so here's my standard, here's my polarization.
Yes.
And then given that one, any other element of the Néron-Severi group is like some other ellipsoid.
Yes, yes.
There's like some stretching transformation that maps the first ellipsoid to the second.
Yes.
And so then the idea is that we can.
I think I want to call that a transvection or something like that. Transvection operator. Go ahead.
Good. I was looking for a good word for that.
Yeah.
Okay. So then the point is, I guess one of the points is that if I have two different elements of the Néron-Severi group, I get two of these, so I get two transvections.
Yes, yes.
And I can just multiply those. Let's see, how does it work? I'm getting confused. There's a way to, there's a kind of, I am getting confused. There is a kind of way to compose. Oh, I know what I can do.
You probably want to Jordan bracket them or something, but go ahead, yeah?
Yeah, I want a kind of Jordan-y thing. But I think what I'm saying is that like, I can take there's a transvection that carries H to H prime. Carries, and when I mean H to H prime, I mean like maps this ellipsoid to that ellipsoid.
Yes.
And then I can see what that transvection does to my ellipsoid H double prime. So like here, I'm taking this circle and I'm stretching it out. I can apply that same transformation to H prime, H double prime. And I'm stretching out this big ellipsoid and getting some other big ellipsoid. And so that's like a way for one ellipsoid to act on another ellipsoid.
Yeah, yeah. You're trying to lead up to this quadratic Jordan thing. Go ahead, yeah?
Yeah. So I'm probably getting like some of the details wrong, but that's like some kind of Jordan product.
Yeah, yeah, yeah. I mean, it's like, yeah, yeah.
And that's so that's what it is. So the idea is that like, yeah, and it's nice to think about now when you start thinking about the integrality conditions, it gets a little bit more tricky because like you could have like, well, it's hard to know like what condition your transvection should obey to map one of these integral ellipsoids to another integral ellipsoid.
I haven't thought about that much, but okay, go ahead, yeah.
But it turns out that what people often do right around this time, although none of them say it this way, but when the people are
Yes.
studying this stuff, what they do
Yes.
is they conveniently tensor the Néron-Severi group with the rationals.
Yes.
And so
Yes.
basically that's, I think what that is exactly just enough to like not have to worry about that question.
Yes.
So then you, I mean, you don't have to go all the way to like the reals. But
right. In particular, if, well, but yes, but I mean, if you're just concerned about the rank, then it's probably harmless to tensor with the rationals.
right. But what's not so I mean, what's cool,
Yeah.
I mean, so what is what's harmful about tensoring with the reals
Yes.
is that I believe the classification of the Jordan algebras over the rationals is much more fine-grained and interesting than over the reals. So
Right.
like,
yes, but that sounds like both a good thing and a bad thing.
Yeah. So I mean, over the reals, I understand it pretty well. And
right. This is where you're trying to teach me about Brouwer groups and stuff like that.
right, exactly. So like the Brouwer groups of the rationals is much more subtle, but then that like people like, of course, algebraic geometers are going to like all those subtleties because that will like let them get more fine-grained classification of abelian surfaces, basically. But a good crude classification is just to like think about the Jordan algebras after we tensored with the reals, and then these ellipsoid pictures sort of are basically all there is. Well, they're all there is to it. You have to see like which Jordan algebras actually.
Yes.
And the only ones that come up are pretty non-exotic, are the non-exotic ones, the matrix algebras over the reals, complexes, and the quaternions. I mean, so that's like mildly exotic.
I mean, we're getting really close to the point where I'm tempted to try to get you to display on the screen the email where you sort of set out a table, sort of informally classifying the different Néron-Severi ranks.
Right.
Are we getting that close to that point yet? I mean, we're not actually going to do anything with that, but it'd be nice to just display that.
I can show it, and I can sort of talk through why I made that.
Yes.
Yeah.
Yes.
I'm excited enough that I don't mind if we're running over, so I'll do it.
I can't. Oh, maybe I can. I'm sort of low tech here, and I didn't have a clock, but maybe I actually do have a clock here. So it's okay. We're a little bit over, but okay. Go ahead.
So I'll find that email. Yeah. So my basic guess is that for the kind of examples of abelian surfaces that we've been most talking about, we at the Jordan algebras that we'll get once we tensor them with the reals is just going to be this special relativity example. Just 2x2 self-adjoint complex. Matrix. And so then my belief is that like when we want to understand that at a more refined level.
I was gone?
I'm still on.
Oh, sorry.
Okay.
Oh, man.
Sorry for the introduction. Go ahead.
It's okay as long as he doesn't insult me.
He probably wants to, but go ahead.
Do you see this email?
Yes, I don't see the full list there. Now I see the full list. Yes.
Yeah. Okay.
And we think the full list isn't really full. We think there are some missing, perhaps sort of missing cases or something.
Right. Yeah.
But it's very representative of the coarse, rough behavior.
Yeah, let me take an example of one here.
Yeah.
So like, let me think about like the Gaussians. Well, let's like do like the Gaussian elliptic curve times the Eisenstein elliptic curve. That weird.
Like I sort of hinted at the beginning, that's the one that should be really useful to us. But since it's going to be so useful to us, let me talk about a couple of the other different ones. So you've got 5 and 6, the square of a generic elliptic curve and the square of a non-generic one. And you're suggesting that there's a rank difference there, rank 3 versus rank 4. And that looks really suggestive and interesting. It's making me, what is it making me think of? It's making me think of like, what am I trying to say? That, you know, like when we were fooling around, certainly when we were, right? You had this frontispiece on some YouTube videos that you displayed or something like that, where there was this picture of this,
yeah, that was for the Gaussian squared.
Right. And so that was like, that really had to do with this Minkowski 3+1 space-time and its full Lorentzian group or something like that. And yeah, but that was over the Gaussian integers. But if you just compare it over to the ordinary integers, then you'd be getting this, you know, instead of SO3 comma 1, you'd be getting like S over SO2 comma 1 or something like that. And so that, I mean, I have the feeling that when I understand this, that will directly correlate with what you're saying here, that SO21 for the automorphism, right? I mean, for the, right? Right. Somehow I'm saying, I mean, you're talking about you're hinting or saying all about the endomorphism ring of these abelian surfaces. But even if I just take the automorphism group of these abelian surfaces, I see a very gross distinction here between the square of a generic elliptic curve and the square of the Gaussian one, right? You get this,
right.
Yeah, so I don't completely understand that yet, but it really seems like it's going to connect with what you're saying. But sorry, that was an interruption. You were trying to get to the.
So like, I mean, so one point that I actually secretly made, is that the way that the endomorphism algebra of the abelian surface shows up is
Well, you already said. I mean, you know.
Okay.
Go ahead. Go ahead.
I actually didn't say that, but
okay,
yes,
but you really hinted. Go ahead.
Yeah, so you got it. Okay, maybe you got it. So right. So the endomorphism algebra of the abelian surface, like when you tensor it with the rationals, then it will be a Jordan algebra over the rationals. And so we sort of, and we can understand it in a bunch of these cases. So yeah, I'll just do one case and then quit. And so like, you know, let's do like the Gauss. So like, okay, I'll do two cases. The Gaussian squared, the Gaussians times the Gaussian.
Yeah.
So then the endomorphisms are going to be like 2x2 matrices with, in the 2x2, the endomorphisms will be 2x2 matrices with entries in the Gaussian integers. And if we would like tensor the rationals, it's like 2x2 entries with 2x2 matrices with entries in the Gaussian field.
Yeah, somehow when you tensor with the rationals, you really do get closer to directly connecting with the automorphism group or something like that. But sorry, go ahead. Go ahead.
And so then if you look at the so if you imagine a 2x2 matrix with entries in the Gaussians, then the self-adjoint ones, well, it's just like the usual notion of self-adjoint. So the diagonal entries have to be real. So they have to be integers. Let's do it for the Gaussian integers, just to talk.
Yeah.
So the two entries there have to be integers, but then the off diagonal entry can be anything. And so it can be any Gaussian integer. So you get two more integers out of that. So you get a total of 4. You get a rank 4. You get a rank 4. So the endomorphism algebra as an abelian group, the endomorphism ring as an abelian group is just a rank 4.
That sounds right.
But now let's like do the same thing, but with like a generic elliptic curve.
Okay.
So now the only endomorphisms
Right.
we're going to get for the square of the elliptic curve are just 2 by 2 integer matrices.
Right. Right. That sounds right. That sounds right.
And so now the diagonal entries have to be an integer like they were before. When we look at self-adjoint ones, the diagonals have to be an integer. And the off diagonal now would just have just one integer there in the off diagonal. So now we're down to 3, a rank 3 thing. So that's sort of how this game, well, that's part of how this game.
That sounds really great. That sounds really great. Maybe my biggest problem at this point is that what you're saying is so much like what I was expecting that it's hard for me to check and see that I really understand that it's correct. But yeah, this seems really good. This seems really good.
So, yep. I'll just say one more. When you've got like two different generic elliptic curves.
Yes. Yes.
The endomorphisms are just like multiplication by z on one of them or multiplication by z on the other one. So you can think of those as just like diagonal matrices. If you want to cling to this 2 by 2 matrix picture.
Yeah, those have just a very slightly bigger automorphism group than usual. Because you can take the inverse automorphism on each factor separately. But that's just very slightly bigger, I think, than the but somehow at the endomorphism ring level, it's going to be a full extra rank, according to what you're telling me. I'm not sure I completely visualize that yet. You're trying to tell me how it works? Yeah.
Yeah, you look at each factor and you can there's the automorphism of multiplication by any integer on each factor.
I guess that's right. I guess that's right. So, right. So that's right. You can do each factor separately and you can, yes. So what I was saying was that if you want the things that you're describing, those endomorphisms to be invertible, then you're sort of stuck taking those diagonal entries to be -1 or +1 or something. So you only get a few extra automorphisms. But if you're doing the endomorphism ring, then they don't have to be, you don't have just the two choices of 1 and -1. And so you get a whole extra rank in the endomorphism ring. I think that's what you're telling me.
Yeah. Yeah. So that's, so that you can do
That's right. That's right. That's right. That's right. So that's right. For the product of two distinct generic elliptic curves, you can rescale or whatever each factor separately, and that's giving us an extra rank in the endomorphism, right?
Yep. Yep.
Okay, so that's very good. That's very helpful. That's very helpful. So again, I think it's going to be really, it seems like we get this really easy example of the Gaussian Cartesian product, the Eisenstein one. And that should be really
I was sort of intimidated. I was sort of a little scared of actually working out all the details, but now that I've did this baby case of Gaussian times Gaussian, I think I just see how you adjust it, and so I don't think it should be so hard. Yeah.
I mean, I've been interrupting a lot, but I still want to. I want to even more later at some point. I want to.
It's called talking.
I've got, there are a whole bunch of viewpoints to view this Néron-Severi group, and you're describing some good ones, but Depending on how ambitious we get, I may try to throw a couple of viewpoints, a couple of extra viewpoints into the mix, which are secretly, all these viewpoints are secretly equivalent. But like, I'm thinking of like, one of them is a little bit fancy is, think in terms of Hodge structures and stuff like that. But then there's also other viewpoints which are very concrete, which help me, I think. But anyway,
Yeah, anyway, I've gotten out of my system the stuff that I
yes,
built up so far. So
yes.
so you're welcome. I mean, I'd be happy to hear about that stuff next time.
Yeah, I'm not sure what we'll try next time, but I mean, we have so many things. We have so many things to do. But yes, but
quite possible that by next time I'll have worked out that Gaussian times Eisenstein thing, and so I think it won't take that long to explain actually once it's done. So
I mean, I may take a stab at that too. Maybe trying to make a lot of guesses about how it's going to go. But all right, okay. So this was very helpful. Is there anything else we're trying to do before we quit? I'm sorry, I already kept you over time.
Yeah, no, I think it's fine.
Okay. I guess we're ready to quit here.
Yep.
So thanks a lot.
Okay, great. That was a lot of fun.
Okay, bye.
Yeah, see ya.